When an object travels along a circular path at constant speed, it is said to be changing its direction as it moves around the circle. Because acceleration is defined as the change in velocity, therefore a change in direction of velocity also constitutes acceleration, just like change in magnitude of velocity does. Mathematical assumptions are made for uniform circular motion, in order to define that its acceleration is pointing towards the center of the circle, called centripetal or radial acceleration. By means of derivation, scientists came up with this equation to solve the radial acceleration for an object at certain constant velocity and radius. This relation shows that the greater velocity, the faster the velocity changes direction. The greater the radius, then the lesser velocity change in direction. In uniform circular motion, the velocity vector is perpendicular to the acceleration vector, thus they are not same in direction. Unlike free fall motion where velocity and acceleration are parallel, and indeed the same in direction. When an object is accelerating, it must have a net force acting on it. So, an object moving in circular motion, which is accelerating, must therefore have a net force applied to keep it moving. Since the centripetal acceleration is equal to v square over r, the force of an object in circular motion is equal to m times v square over r. Remember that at this instance, acceleration is directed towards the center of the circle, hence, the net force is directed towards the center of the circle too. This is called the centripetal force, which basically means that its direction is pointing towards the center of the circle. But have you heard about centrifugal force? If you do, it is a common misconception that there is an outward force acting on a revolving object called the centrifugal force. There is actually no real centrifugal force. The reason why is to be discussed in my next video. Click follow and keep updated for more physics discussions. Centrifugal force is a common misconception that an object moving in circular motion has an outward force acting on it. To prove that there is no real centrifugal force, consider this. David is swinging a stone using a slingshot to defeat the giant Goliath. He feels that there is an outward force pulling on his hand. Here's when the misconception arises that this pulling force is interpreted as the centrifugal or outward force. The truth is, David pulls the slingshot inwardly to keep the stone in a circular motion. The slingshot exerts this force on the stone. The stone then exerts an equal and opposite force on the slingshot, in accordance with Newton's third law of motion. The stone exerting an equal and opposite force is the outward force that David feels in his hand. To see even more the evidence that centrifugal force does not exist, when David let go of the slingshot, the stone flies off tangentially, in the direction of the velocity at the moment it was released. Goliath was hit by the stone in the center of his forehead. If centrifugal force existed, the stone would fly outward and David would miss hitting Goliath. He would not defeat or slain the giant. As a conclusion, centrifugal force does not exist in objects moving on circular motion. It's the third law of motion that answers the question, and explains why you can feel an outward force in your hand when swinging any object. You can try this simple experiment and find it out yourself. Thank you for watching. Wanna see more videos like this? Click follow and stay connected for new upload. In a circular motion with constant magnitude of speed, the net force of an object is directed towards the center of the circle. But if the speed is not constant, or if the speed is changing, either increasing or decreasing, then the vector force is not directed towards the circle, but only its components. To illustrate, only its component, the centripetal force, is directed towards the circle. Accordingly, the component of its acceleration, the centripetal acceleration, is also directed towards the circle. The vector force also has a component tangent to the circle. This increases or decreases the speed of an object in non-uniform circular motion. Also, there is acceleration tangent to the circle, in accordance with the tangent force. Tangential component of acceleration is equal to change in velocity over time. While centripetal acceleration is equal to velocity square over radius, the two components are always perpendicular to each other. Their direction continually changes as it moves along its circular path. To find the total vector acceleration, the two components are sum up. Since the two components are perpendicular to each other, the sum is equal to this equation. This is an application of the Pythagorean theorem. This concept can be used in problem solving, such as objects moving along a curved path. A portion of a curve can be treated as an arc on a circle with a radius of curvature. At this point, its velocity is always tangent to the circular path. Here's an example for this concept. A race car starts to accelerate from rest to a speed of 35 meters per second in 11 seconds, on a circular track of radius 500 meters. Find the tangential acceleration and the radial acceleration at the instant when speed is 15 meters per second. To solve this, recall the equations for tangential acceleration and radial acceleration. Substitute the given to the equation. The tangential acceleration is 3.2 meters per second squared, while the centripetal acceleration is equal to 0.45 meters per second squared. Thank you for watching. Please click follow if you want more videos like this.